Quantum theory is regarded as one of the greatest advancements of modern physical and chemical sciences of the 20th century, providing deep insights into the nature of matter and energy. Because of its abstract nature and requirement of knowledge of higher-level mathematics, quantum model remained as a challenging subject for students as well as teachers. If you keep it simple to explain, you literally make the subject dilute. If you go deep in the subject, it looks overwhelming. In this video, we shall break down the topic into small pieces of knowledge, and as we go further, we shall link these together to understand the big picture of quantum model of the atom. In our schools, we studied the theory of physics using the principles of classical mechanics. Classical mechanics is the physics of large-scale objects governed by Newton's laws of motion. It deals with concepts like force, mass, acceleration, momentum, etc. Classical mechanics treat energy and matter as continuous quantities. Here the objects are tangible, movement is measurable, and behavior is predictable using classical mathematical models and equations. But in quantum mechanics, we study the physics of the very small intangible objects like atoms and subatomic particles. The behavior and properties of the small objects cannot be observed or measured directly as in classical mechanics. Even the extension of the classical theories and mathematical equations to subatomic particles proved to be not correct. So the scientists who initially started studying the behavior of subatomic particles using the model of classical mechanics started getting convinced that there is something missing in the approach of dealing with physics and chemistry of subatomic particles. Still, the question remains, why the principles of classical mechanics cannot be applied to micro-level particles like electrons? Why the physics of the very small objects like subatomic particles need a different approach? To answer this question, we have to understand de Broglie hypothesis, which states that all matter, big or small, exhibit dual nature, meaning that all matter behaves like particle and wave depending on the condition. What does that mean? When the size and mass of the particle is measurable by humans, the de Broglie wavelength lambda equal to h upon mv is so small that, forget measuring the wavelength, it is beyond the perception of a human being. For example, de Broglie wavelength of a particle of mass of 1 milligram moving with a velocity of 1 kilometer per second will have de Broglie wavelength of approximately 6.6 to 610 to the power minus 33 meters. This is an incredibly small wavelength, which is why we don't observe wave-like properties for macroscopic objects. On the other hand, where the size and mass of the matter is very small, like that of an electron, the de Broglie wavelength is very small and comparable to the size of the matter itself. And under such conditions, behavior of particles as a wave is observable. As an example, for an electron orbiting around the nucleus in the ground state of hydrogen atom, the Bohr radius A0 is approximately 52.9 picometer, and its de Broglie wavelength is approximately equal to the circumference of its orbit itself, which is 2 pi A0, which is equal to 332.5 picometer, which is significantly larger compared to that of 1 milligram mass moving with 1 kilometer per second speed. That is why we are able to observe wave properties of a moving electron. Electron diffraction experiments have provided strong evidence for this wave-like behavior of electrons. When a beam of electrons is passed through a crystal lattice, the electrons scatter and produce a diffraction pattern similar to how X-rays diffract. This pattern can only be explained by considering the wave-like nature of electrons. Electromagnetic energy is not continuous. Max Planck, in his landmark theory, proposed that energy and matter exist in discrete, indivisible units called quanta, which is described as E equal to h into mu, where E equal to energy of a photon, h is Planck's constant, and mu is frequency of the wave. This theory in principle is in contrast to the theory of classical mechanics, where the energy is considered continuous. Einstein's explanation of photoelectric effect provided enough evidence that energy exists in discrete form in electromagnetic waves. The entire spectrum of electromagnetic waves, like radio waves, X-rays, infrared, visible light, ultraviolet rays, exhibit the property that energy is in packets of discrete quantities. Here we are highlighting dual nature of particle, quantum energy and uncertainty principle again and again to emphasize the fact that this is the foundation on which the entire theory of quantum mechanics is built upon. The word quantum is derived from the Latin word quantus, meaning how much. In the context of quantum mechanics, quantum refers to the idea that energy and matter exist in discrete indivisible units This concept is in stark contrast to classical physics, which treats energy and matter as continuous quantities. Even though quantum mechanics is fundamentally different from classical mechanics, the term mechanical is retained to emphasize the idea of a model as systematic way of understanding and predicting the behavior of a physical system. While quantum signifies a departure from classical mechanics, mechanical underscores the model building aspect and the aim to predict and explain the behavior of atoms and subatomic particles. What is quantum mechanical model? Imagine an atom as a tiny solar system. In the center, there is a nucleus like the sun, and around it, electrons orbit like planets. But unlike the solar system, where we can pinpoint the exact location of planets, we cannot do the same for electrons in an atom because wave nature of the electron inside the atom cannot be neglected. One of the strange things about electrons is that they behave both like particles and waves. Sometimes they act like tiny balls, particles, and other times they behave like waves, spreading out and interfering with each other. To understand this strange behavior, scientists use a mathematical model called Schrodinger equation. It is a bit complex, but it helps to calculate the probability of finding an electron in a specific region of space. The Schrodinger equation is a mathematical equation that provides a way to calculate the wave function of a system. The wave function contains all the information about the system state. There are two forms of Schrodinger equation, the time-dependent and the time-independent. For quantum mechanical model, we use time-independent model of Schrodinger equation. Wave function describes the probability amplitude of finding a particle in a particular state. The square of the wave function's absolute value gives the probability density. Hamiltonian operator represents the total energy of the system, including both kinetic and the potential energy. Eigenvalues and eigenfunctions. Solutions to the Schrodinger equations are eigenfunctions and with the corresponding eigenvalues, which represent measurable quantities like energy. The quantum mechanical model paints a fuzzier picture. Instead of precise orbits, it talks about regions of space where electrons are most likely to be found. These regions are called orbitals. Think of them as clouds with denser parts indicating a higher probability of finding an electron. The quantum mechanical model of the atom is based on quantum theory, which states that matter has properties connected with waves and other particles. The model describes electrons in an atom as waves rather than particles. The model is based on probability rather than certainty and indicates the likelihood of finding an electron in a specific region of space. The model is based on Schrodinger's wave equation, which can be solved to yield a series of wave functions. The square of the wave function represents the probability of finding an electron in a given region. An atomic orbital is a region within an atom where there is a 90% chance of finding an electron. Electrons are organized into shells based on their energy, with higher energy shells being farther from the nucleus. Shells are further divided into subshells labeled with the letters S, P, D, and F. Electrons have an intrinsic property called spin and can have one of the two possible spin values, spin up and spin down. When an electron moves from one energy level to another, it absorbs or emits photon. In this video, we are neither interested in how Schrodinger formed his equation using wave function nor how to solve the equation. Rather, we will be focusing on the solutions of the wave function provided by Schrodinger for configuring electrons in an atom with multiple electrons. What are quantum numbers? Quantum numbers are solutions of Schrodinger equation which describe the location and energy of an electron in an orbital. Every electron in the atom has a set of 4 unique quantum numbers: the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin quantum number. Note that these quantum numbers are not independent of each other. The principal quantum number is a positive integer that indicates the energy level or a shell of an electron. The principal quantum number of an atom corresponds to the row number of that atom on the periodic table. For example, the top row of atoms has a principal quantum number of 1, the second row has a principal quantum number of 2, and so on. The principal quantum number indicates how far away an electron is from the nucleus. Electrons with larger values of n are farther from the nucleus and they are easier to remove from an atom. In an electron configuration, the principal quantum number is written before the s, p, d, or f. For example, in the electron configuration of lithium, 1s2, 2s1, The one before the S2 indicates that those electrons are in the first shell, and the 2 before S1 indicates that the electron is in the second shell. The angular momentum quantum number L describes the general shape or region of an electron's orbital. It is also known as the azimuthal quantum number or secondary quantum number. Different values of L correspond to different shapes such as S, P, D, and F orbitals. For a principal quantum number n, the lowest possible value of L is 0 and the highest possible value is n-1. For example, if n equal to 2, then L could be either 0 or 1. The spin quantum number describes the spin of the electron, which can be either up or down. In each orbital, there can be one electron with a spin up and another electron with a spin down. The diagram shows shapes of S, B, D, and F orbitals. S orbital is spherical in shape and has no suborbitals. P orbital is dumbbell shaped and has 3 suborbitals. D orbital looks a bit more complex and it has 5 suborbitals. F orbital is very complex and it has 7 suborbitals. These orbitals are oriented around the nucleus along X, Y, Z axis. Electron configuration or arrangement of electrons in an atom depends upon the total number of electrons present in the atom. The diagram shows for a given principal quantum number n, how many orbitals are possible, and for each orbital, how many suborbitals are possible. For example, for principal quantum number n equal to 1, there is only s orbital. For n equal to 2, there is one s orbital and one p orbital. In p orbital, there are 3 suborbitals. For n equal to 3, there is one s orbital, one p orbital, and one d orbital. P orbital has 3 suborbitals, and d orbital has 5 suborbitals, and so on. Each orbital can accommodate 2 electrons, one spin up and one spin down. The order of filling starts from the lowest energy to highest energy level until all electrons are configured. To configure electrons in multi-electron atoms, we follow specific rules and principles. Aufbau principle: electrons fill orbital starting from the lowest energy level to higher energy level. The order of filling is 1s, 2s, 2p, 3s, 3p, and so on, as shown in the diagram. Pauli exclusion principle states that no 2 electrons in an atom can have the same set of 4 quantum numbers n, l, ml, and ms. This means that an orbital can hold a maximum of 2 electrons with opposite spins. Hund's rule states that within a subshell, electrons fill orbitals singly before pairing up. All single electrons in a subshell have the same spin. Example: we shall consider configuring a carbon atom. Carbon has 6 electrons. Let us fill the orbitals following this rule. 1s orbital. The first 2 electrons fill the 1s orbital. 2s orbital. The next 2 electrons fill the 2s orbital. 2p orbital. The remaining 2 electrons fill up the 2p orbitals. According to Hund's rule, they will occupy different 2p orbitals with parallel spins. So the electron configuration of carbon is 1s2, 2s2, 2p2. And in the diagram, you can see the visual representation of electrons in each orbital. What is the size of an electron? Electrons are often described as point-like particles, meaning they have no measurable size. The theoretical value calculated based on classical electrodynamics and is approximately 2.179 10 to the power minus 15 meters, but this is not a physical radius in the traditional sense. In reality, the electron's true nature is more complex, influenced by quantum mechanics, where electron is considered as a wave. Because of extremely small mass, can we accelerate an electron to a speed comparable to speed of light? Yes, it is possible to accelerate an electron to a speed of very close to the speed of light. This is precisely what particle accelerators like the Large Hadron Collider do. However, due to the principle of special relativity, no object with mass can ever reach the speed of light. As an object approaches the speed of light, its mass increases, requiring more and more energy to accelerate it further. This phenomena ensures that speed of light remains a cosmic speed limit. With this, we have reached the end of this session. Thank you for watching.